Thank you for joining me for methods of dealing with time series data problems for data scientists, essentially. A bit of a mouthful of a talk here, but hopefully the content will be useful for you and sort of elaborate on some of those queries that you might have with handling time series data with algorithms and forecasting of that data. So my name is Clifford, and I'm a developer advocate at InfluxData. So in my past life, I was a sales engineer for industrial IoT solutions. I have a passion for autonomous and vision-based projects. I try to make my IoT accessible to all, and my belief is that industrial IoT success belongs to the domain experts. So you might be wondering, why is an IoT specialist given a data science talk? And what I hope to convey to you today is that people from different sectors using InfluxDB tools can slowly learn and understand how we can use common data science practices within the InfluxDB platform to achieve new results of our data, new data enrichment with the InfluxDB platform. So we've got quite a bit to cover today. So my idea is to break it into 4 parts. I'm going to give you the idea of what InfluxDB and Telegraf is in a nutshell. We're then going to discuss forecasting and anomaly detection with Telegraf, which is our open source metrics agent. We're then going to look at data analytics, lifecycle management, and MLOps with Flux. And finally, we're going to look at integration with Zeppelin and Jupyter notebooks, as well as discussing some favorite data science libraries that me and the team have come up with working with time series data. So first, what I wanted to do is, if you haven't heard of InfluxDB and Telegraf, let's just quickly have a fireside chat of what it is. So the InfluxData platform can be split into 2 main areas, Telegraf and InfluxDB. Telegraf is our open source collection agent. Essentially, you can collect from just about any data source, parse that data from any data format, aggregate that data, and send that to pretty much any other platform you're looking for. We have around about 300 plus plugins now to date, and it's completely free, open source to use, and most of the contributions come from our amazing community. So you have plugins such as standardized HTTP, you have syslog plugins, you have plugins for Apache Kafka, Kubernetes, you even have industrial-based plugins for such as MQTT, Modbus, OPCUA. You also have output plugins for a variety of different storage engines, not just InfluxDB. We also have output plugins for our competitors too, MongoDB, and as well, to name a few. And just to let you know how open source it is, anyone can contribute plugins here. So the next part of our platform and the core part of the InfluxDB platform is InfluxDB itself. And so at its heart, it is a dedicated time series database. And what we mean by that is it's great at storing data with a timestamp. So on average, we're 3 to 5 times faster at ingesting data than other NoSQL solutions. And we also store data on average 5 times more efficiently than other NoSQL database solutions as well. Where InfluxDB stands away from other time series databases is the services that we build on top for you to use alongside your time series data to get the most use out of building your applications. And so what do I mean about getting the most use of building your applications? Well, that's down to visualization, that's down to using our data analytics and query engine to perform high fidelity querying of your data, and basically further analytics, and also our task engine for automating tasks on your data, such as alerting, threshold checking, and other things like this as well. So today we're going to first discuss Telegraf and how you can use Telegraf for forecasting and anomaly detection. So for this, I wanted to paint a bit of a picture. So Luke, one of our InfluxData engineers, who uses InfluxDB to monitor his home brew setup. So the data contains temperature for 2 beers, very adequately named, Haze_V5 and BV_V1. And they're sort of early in their fermentation process. So at this point in the fermentation process, it's important to keep the temperature constant. So what you can see is with the two arrows. So on the one on the left, sorry, normally I'd like to be able to point at this and go over here, you can see a temperature gauge. And so what we're doing is we're using OCR to read the temperature of this and ingest that using Telegraf. On the secondary side, you'll see a bucket. And that bucket is where Luke would place ice in to keep the temperature consistent in his fermentation process. So Luke basically asked us, how can you help me keep my temperature consistent with the data that I have? Now, this is an IoT use case, but please keep in mind that this is relatable and can be used across industries. We're going to discuss a very generalist forecasting technique in order to help Luke out here. So the objective is to use Telegraf with the ExecD processor plugin to help Luke maintain the consistent temperature of his beer. The two things that we're going to do is forecast the temperature so that Luke can better regulate the temperature of his beer and be notified in advance if we need to add ice. And the second is calculate the prediction residuals so that Luke can be alerted when there's anomalous behavior in his beer. So like a bad OCR read or bad thermometer reads that we see in the data. So let's have a look at the data itself. So this is the raw temperature data that we're seeing from Hayes_V5 and BV1. So through visual inspection, we make the following observations about our data. Forecasts need to be generated almost immediately because spikes in beer temperature occur almost immediately. So there simply isn't enough data for us to train a neural net, for example. And there's no clear seasonality present, so thereby excluding other classical forecasting techniques, such as autoregressive integrated moving average and ETS, or exponential smoothing. So these we can take out from our consideration. What we decided to do instead was use double exponential smoothing, which we call Holt's method. So we selected this under the following pretenses. Essentially, Holt's method requires little data. It can be as small as 10 points worth of data to generate a forecast. It requires no seasonality within the data. It's computationally efficient, so it's really easy for us to process on our data in real time. And it's extremely accurate with univariate, or data basically with one variable for basically running over a time series data. And just a fun fact for you, I put it in like the yellow at the bottom. You'll see that like there's a runaway temperature at the bottom for B_V1. That's either a really bad OCR read or the house is on fire. Could either be one or the other. We just don't know. So let's talk about how we can use the ExecD processor plugin in order to basically forecast for our application. So to understand that, basically Telegraf has a series of plugins. You have ingestion plugins, you have aggregator plugins, and you have output plugins. One of the processor plugins is called the ExecD plugin. Now what the ExecD plugin is, it allows you to run a third-party application or script. So you can basically ingest data, send this to your custom script, write that data back into Telegraf and send it to any platform of your choice. So you can see that here. So we essentially are using basically metrics to ingest in. We send those to our application. We run our your application logic, print that, and bring that back in through standard out back into Telegraf where we send it on. So as you can see, Telegraf is purely configuration based. So there is a no-code solution to use Telegraf. You just have to be able to work with it with basically a configuration file. And you can break that down into sections. So for example, the agent is how we work with the overall Telegraf agent and carries basically global settings. So you can see here, interval is the period in time we collect our data. Metric batch size is how many samples we'll take in before we basically push our data through Telegraf. And metric buffer limit is how much data that can sit in the Telegraf queue before we start dropping metrics. So that's great if you have a network outage and you can store metrics over a period of time and then send data on after that. Next, you'll see input plugins. So in this case, we're actually using an exec D input plugin, because since we don't have the brewing kit available to us here today, we're just going to use a simulator. So we're going to run that simulator using the input exec D plugin, and that is going to pump metrics into Telegraf. Next, you'll see the processor exec D plugin there. And what you can see it's doing is calling a Python forecasting application. So this is just a simple forecasting script that we wrote, which I'll go into detail in 2 minutes. And lastly, you can see the output plugins. The output plugin, in this case, we're going to be pumping our data into Influx, of course. So just to give you an idea of how simple it is to write your own logic, if you're writing a Python application, this is the only wrapper code you need for it to work with execd. You essentially need to ingest the line data through standard line in, pipe it into your program, run your standard or your custom logic that you want to do, and then pump it back out using standard out flush. Simple as that. So let's get into the juice of the forecasting application. So in order to produce a forecast, we needed to micro batch our data, and then we're going to use halts to fit and then also forecast that data. So essentially the application is going to work like this in bullet points. Read points in through standard line in. We're going to pass that data, accumulate the points into a mini batch, continuously generate a forecast for each point in standard in, continuously calculate the residuals. So basically we're going to use the residuals to have a look for anomaly detection based on our prediction and the next temperature sample coming in. And then we're going to send that data back to Telegraf before it goes to InfluxDB. So what you can see here is the bulk of us using forecasting. So what we decided to do for using this Python application is we used a library called stats model. So this is a Python module that provides classes and functions for basically estimations with many different statistical models, as well as conducting statistical tests and statistical data explanation. So essentially what we can do is we can call the stats model halt method directly from this library in order to fit our data and then forecast upon that data. So essentially what we're doing is double exponential smoothing. And so what double exponential smoothing is an exponential weighted average of trend and values of data together. So we can see where they're basically, so we can basically use that to work out the trend of seeing whether, okay, my next prediction of the temperature is within this range compared to my actual expected value of temperature coming in. And we're going to use that in order to regulate and say whether more ice should go in or not. So what you can see is, if I can just jump down and fill it back. Can you hear me now? Okay, yeah, sorry. So you can see here within the code that essentially using the forecasting technique with this library is pretty simple. Essentially all you need to do is we're going to use the fit.forecast here with our prediction. Oh, thank you. Are we okay? Can you hear us now? Fantastic. Okay, this might be better so I can literally just go through the code a little bit more. So essentially what we're doing is we're collecting our data at this point and we're creating a pandas data frame. So we're basically converting our metrics into a pandas data frame. We're collecting that pandas data frame into those micro batches of data. We then call our halts function to fit the data. So you can see that as simple as calling the halt stamp trend here. And then we fit that data using fit.forecast. And then we can generate our forecast from that data. So really simple minimal code from that library just to generate that data. And then we pass that data back into InfluxDB. What we're doing here is we're also calculating our residuals. We're basically taking the last value, the last real temperature value coming in, and we're looking at our prediction, our forecast, and we're basically subtracting that and saying, hang on, how far are we away from our actual prediction? And if our prediction is 3 to 4 points higher, then essentially what we're going to do is we're going to trigger that as an anomaly. That could be anonymous from an OCR point of view. That could be anonymous because there is generally an issue with the temperature. So hopefully that sort of explains the code a little bit better. So after forecasting, you can basically see, if we do this, you can basically see the results of our visualization here. So this graphing is all done by InfluxDB, and you can see that we've mapped both data sets onto we've mapped both data sets in InfluxDB. So you can see in blue is the actual temperature that we got for our brewing. And then lastly, in purple, you have the forecast. So you can see on 10 points, we're actually quite accurate. I mean, there's spots where we've over-predicted, where we consider there to be anomaly, which could be a bad OCR read. And you can see we're actually picking these up within our anomalies here. So we've actually defined, I believe, a count of 6 anomalies that you can see here from the difference. So in terms of just having a minimum of 10 points of forecasting in real time, we're getting pretty accurate results from halts when we have a lack of seasonality and a lack of high fidelity data to run our forecasting on. So keep that in mind when you're looking at algorithms. If you don't have seasonality available to you, there are methods that you can run, especially within our application and others, that still give you great accurate results when looking at your data. So now that we've looked at data in motion, let's have a look at data in rest. So what I mean by data in rest is data that's stored within InfluxDB. So InfluxDB has its own functional processing language. Now I'm not calling it a query language because Flux is so much more than that. Essentially what you can do with Flux is you can analyze and predict upon your data all server side. So this means you can shape, transform, and enrich your data even before it leaves the database and goes into one of your applications. That's sort of the power of Flux, and that's what we're going to sort of describe some of the functionality here today. So Flux has a number of inbuilt functions and tools that you can utilize directly out of the box. You basically just include them like a Python library, and they're one line of code in order to use them alongside your data. So we have transformation functions for statistical time series analysis. So your basic ones, correlation, covariance, standard deviation, quantile, spread. These are all ready to use functions that you can use within Flux. We have transformation functions for dynamic, statistical, and fundamental time series analysis. So we can basically do analysis on the derivative, moving average, double moving average, exponential moving average, time weighted average, and of course we can actually do double and triple exponential smoothing all directly on database side. So what we've seen before with Telegraf is we actually did Holt's methods out with InfluxDB, but we actually have an inbuilt function within InfluxDB that you can use directly out of the box. So it really depends on your use case and whether you want to be predicting in real time. Sorry. Oh, no worries. You want to be predicting in real time, or you want to be looking at your data over a longer spread of time. And that's the power of using a time series database. And lastly but not least, we also have more specific sort of domain functions. So if you're within the financial industry or analysis, we have this is always a mouthful for me to say. We have Shandy's momentum oscillator and Cotham's adaptive moving average as well. So these are all inbuilt functions. And then we have a basic mass function for iteration and calculation. And then finally, we have geospatial and geotemporal data packages all included within InfluxDB as well. So it's a lot of punch from a data processing language. So what I wanted to do was really delve into one function that we have within Flux, which is anomaly detection. So we can actually perform medium absolute deviation directly on our data within InfluxDB, and MAD for short. And so this is basically to look at data that's deviating away from the pact. So if you have a look at this example here, this is all server data, basically looking at disk inputs and outputs. And as you can see with this data, it's really hard to see which server is underperforming. So which server is anonymous compared to the other servers that you're monitoring. what you can do with MAD, or medium absolute deviation, is you can look at derivatives in this data and see which timestamps or which data points are deviating from the rest of the path. So, spoiler alert, within this, we can actually see the purple line here is our deviator. So this is where MAD would consider a deviating factor within our data. And what I'm going to do now is I'm going to break into you what the Flux code looks like for that. So this is Flux. Yeah. So this is Flux. Now, I don't expect all of you to get this straight away. This is the Flux language. This is sort of what I play in every day, but this is something you can learn. So when we call the MAD method, so basically, I love to say it, but we call the MAD method, or the medium absolute deviation method, this is the code that's actually being called in Flux. You're calling one line, but this is the library code behind, and this is all written in the Flux language. So what I wanted to show here was for you not to understand the Flux logic, but to basically sort of understand how you can actually process data within a language that's not just like SQL. Because SQL, we're querying, we can do maybe some form of slow aggregations or analytics, but here we can actually derive new enrichment from our data, all from the Flux language. So, last but not least is, if you didn't want to do all of your work inside InfluxDB, we also have integrations into Zeppelin and Jupyter notebooks. So Jupyter notebooks, we have a Flux interpreter. So basically you just pip install the Flux language, and what it will do is you can run your Flux logic directly. So if I jump down again, you can see in this case with our Flux logic, we're calling from our bucket, which is our database. We're taking a range of data over the last day. We're then filtering for our measurement CPU, our field, which is our usage per user, and then we're filtering for these fields CPU1 and CPU2. And essentially what we will do is we'll automatically transform the data retrieved from our database into a pandas data frame. So it's easily integrated into any of the analysis and any of the notebooks that you are currently using or working with your time series data. So Zeppelin's even easier. We have a standard integration into Zeppelin. So it means you don't even have to worry about including the Flux language library in. Basically, you define all your parameters in Zeppelin for query in the InfluxDB database, such as URL that you're pointing to, the token, which is your authentication into InfluxDB, and you can automatically query using Flux and retrieve the results using Zeppelin. So pick a tool that's right for you. Some people choose Zeppelin, some people choose raw notebooks. It's up to you how you want to deal with your data, and what we try to do is make it approachable to any platform that you like to use. So lastly, we've just thought this was a little bit more interesting, a little bit more fun, is we came together as DevRels and sort of picked 4 different libraries that we think is great for using, basically analyzing your time series data. So the first one we picked was Anomaly Detection Toolkit. So this is basically a package for unsupervised rule-based time series anomaly detection. So it may not work universally for all anomaly detection problems, but choosing a combination of detection algorithms and detectors, you can basically find the algorithm that works for you in detecting anomalies with your time series data. And it's pretty simple and pretty easy to use. The next is FB Profit. So you'll know this from Meta, or Facebook as they used to be called. So this was developed by them. So Profit is a procedure for forecasting time series data and is based on an additive model where non-linear trends fit with yearly, weekly, daily, yearly, weekly, daily seasonality. So this is really good for people that don't have a lot of domain experience in looking at anomaly detection, but basically want to get started. So you basically fit your data into their algorithm and see what the results look like. The only issue that I have with Profit is essentially, so it requires minimal data preparation, but it doesn't always fit everyone's results. You don't really have that much control over the results that you're achieving from that. So your data is almost in a black box. Last two is neural profit, which is a derivative of FB profit. So that's neural network based and is inspired by Profit and also by PyTorch with their ARNet. And that uses neural network methods for looking at your time series data. And then finally, the one I was most excited by is CATS. So CATS is a time series analysis, forecasting, and anomaly detection toolkit. And it's a new library for analyzing time series data. It's lightweight, easy to use, and in general, the framework for generic time series analysis, including forecasting, anomaly detection, multivariate analysis, and feature extraction and embedding. This is one of the best sort of up-and-comers that I've seen, and I think CAT's a really great one to investigate if you're looking at time series data. So, demo time. Let's see if I can see it while we're on the screen. So what we've done is for the brew detection anomaly algorithm, we've actually included all the source code open source. So what I thought I would show you is the full setup so you can see how easy it is to run Telegraf, ingest the data into InfluxDB, and see what the results look like. So if I jump this way, there we go. So what you can see here is, I think if I sort of split my screen, and if I go built-in, yeah, let's go back in built-in mirror. There we go, fantastic. So what you can see in VS Code here, I've pulled the project from our GitHub, our community GitHub, and what you can see is our Telegraf config here. So that's exactly the same Telegraf config I showed you earlier. Essentially, all we have to do is install Telegraf. I point to my Telegraf config, and I'm just going to run this with debug mode active so you can see the data writing. I hit enter, we start our process, and we start writing those metrics per second into InfluxDB. So you can see we're generating a lot of metrics a second, and so they're firing into the buff, and then we write all those into the buffer, and we're firing those all into InfluxDB. So what I'm going to do now is I'm going to navigate over to InfluxDB. And if I jump into our dashboarding here, and I look at our brew forecasting, you can see our data ingest over time. So because I'm using a simulator, our data timestamp is off. This is pre-generated data from that date. So this is the data that you're seeing here. And you can see our raw temperature here. So this is all within the InfluxData platform. You can see our temperature and forecasted data over here. And then you can also see our anomalies on that data as well. And just to give you an overview, essentially all you need to do in order to be able to query this data is use the Flux language. And hopefully if the internet's going to hold up, this is as simple as it is. You can see with our functional programming language, Flux, I've basically said, hey, I want to collect the data from this bucket, I want to take the measurement temperature, and I want to yield that. So that shows a visualization of that data. And as you can see within Flux, you can use variables. So I basically yielded 2 variables to show on my graphing here. So this is a really simple use case of using Flux just to visualize raw data. And through Influx as well as seeing your visualizations, you also have an inbuilt view of all your table of your data as well. So hopefully that gives you a bit of an overview of where you can start with InfluxDB and where you can get sort of going with the Flux language. What I suggest doing, if I jump back, hopefully, cross that one off, slideshow, is if you would like to try it yourself, then we have the Git repository there, so all the source code is available. If you want to learn about InfluxDB and learn and basically be trained on our platform, we have InfluxDB University, which is a free set of courses for you to try yourself and become an InfluxDB certified user. So you can use these with and basically certify yourself with Clarify. You can share these on LinkedIn and with your job posts and on your CV to say you use InfluxDB. And thank you. Any questions? Yeah.